Hi guys, in this video we're going to talk about acid strength based on its structure. So sometimes I'm going to ask you to think about the strengths of acids, but you're not going to have the pKa data in front of you. This can be really important as there are millions of organic compounds and there aren't tables of pKa data for all of those compounds. And so this can be an important way to study acids and bases as well as quantitatively through pKa's, right? So today in this video, we are looking at qualitative methods, right? We know that the lower the pKa, the stronger the acid. When we talk qualitatively, though, we're actually going to be looking at the conjugate base. So we know that a strong acid, say something like HCl, is going to have a weak conjugate base, right? So the chloride ion is a very weak base. And this makes a lot of sense because what makes something a strong acid? It can donate that proton easily. And it can donate that proton easily because what is left behind is stable. So when we think about the term, the term weak, we want to also think of that in terms of stable, right? It's going to be lower energy. It's weaker. Okay, so we are going to be assessing the strength of an acid based on how stable the conjugate base is. How stable is it once the proton is gone, right? So what happens is we see that bond breaks, right? And whatever our base is, we'll pick up that proton and the electrons stay with the chloride, right? So this is how we form our conjugate base. We take away the proton and what is left over now has a lone pair from that bond that broke, right? And then we are going to look at that conjugate base to discuss acid strength. So the first thing that you have to do when I ask you which acid is stronger is draw the conjugate base, right? So make a note of that. Let's see. Assess acid strength. Number one, you're going to draw the conjugate base, right? And so you're going to see us do that over and over again in this video. All right. Now, how can we determine if say we're comparing acids, which conjugate base is going to be more stable? Well, our rules to follow, so rules for assessing stability. So assessing conjugate base stability is easy to remember through the mnemonic ARIO, right? And this is going to stand for atom, resonance, inductive effect, so I'm just going to write inductive, and then something called orbital, which is last. We'll talk about that at the end. So you want to do this in order, so you have to check number 1 first, then 2, then 3, then 4, right? Typically, atom is going to be most important. And what you are looking for is the lone pair that is left after you remove the proton, right? There's actually a little kind of like we're going to put an asterisk up here because there's something that's even more important than this, and that's formal charge. And so we will discuss that as we get into it. But then you're going to go atom. If there is a charge, you're going to look for atom, resonance, inductive effects, orbital. Now, this little asterisk is important because, and Klein, it's not that he skips over it. I suppose it's sort of understood that no formal charge is going to be more stable than formal charge. So if you were comparing two conjugate bases and one has a charge and one does not, the neutral one would always be more stable. So I just like to get this out of the way up front. So for instance, if we were comparing the acid strength of H3O plus versus water. Well, okay, so which is a stronger acid? This is the steps you're going to follow. Draw the conjugate base. All right, so the conjugate bases, I'm going to go right underneath. We're going to remove a proton, and we're going to decrease the charge. So H3O plus becomes H2O. It had a plus charge, now it is neutral. H2O, we're going to remove a proton and decrease the charge, becomes a hydroxide ion. Now, water is neutral and hydroxide has a charge. Neutral versus charge. So in this example, you see this kind of an example come up here and there, but it's more rare. So Klein kind of skips over it right here. However, it can affect your homework later, so I want to make sure we go over it. Which one of these is more stable? Which one of these is going to give up that proton more easily to make this conjugate base? Well, this one's more stable, right? It's neutral. This is your weaker base, right? Water is a weaker base than the hydroxide ion. This is going to be less stable, right? It has a charge. It's going to be wanting to reach out and get that proton back more than neutral water would. So this is the stronger base. All right, remember the weaker base came from the stronger acid. So H3O plus is the stronger acid. Right, sorry. And each of the problems that we're going to look at here are going to follow this pattern. We're going to draw the conjugate base. We're going to assess the stability, and the weaker base came from the stronger acid. Now, we don't even have to get into ARIO here because formal charge is going to show itself to be more important than atom, resonance, induction, or orbital. This helps you here when you have a charge, right? If both of the conjugate bases have a charge, what we're wanting to do, charge is inherently less stable. Which one can hold that charge better? And that is where atom, resonance, induction, and orbital will come in. So in this first example, once we get into ARIO, we are comparing butane and propanol. And they tell us which hydrogen to focus on. We're going, let's try that again. We're going with a hydrogen on the first carbon and the hydrogen on the oxygen in the propanol. These are the acids. Which one is stronger? Well, draw the conjugate base. All right, we take away the proton. They're both neutral. Sorry. So this pair of electrons that's represented by that bond stays with the carbon. It was neutral. Now it is a negative charge. The oxygen has two lone pairs when you have a neutral alcohol. When you remove the the proton, you have three lone pairs, right? So we increase the number of lone pairs and we decrease the charge. They both have a negative charge. So we have to decide which one holds that charge more effectively, right? Which one's more stable. And so to do this, you are analyzing electronegativity, right? The more electronegative element is going to be more stable, is more stable with the negative charge. So if we think about our periodic table, right, on the periodic table, row 2, it's boron, carbon, nitrogen, oxygen, fluorine. Fluorine is the most electronegative, and the closer you are to fluorine, the more electronegative you're going to be. Now, this makes it easy to see. Oxygen, more electronegative than carbon. oxygen can hold that negative charge better. Excuse me. No. There's usually 2 sneezes, and of course I gotta catch them while I'm recording. This one is more stable, right, with that negative charge. And this is going to therefore be the weaker base. The weaker base came from the stronger acid. So in this case, propanol is more stable than butane, right? And that's the same thing as described here. Now, what's really important to note, this works. So ARIO has 2 sort of sub-points. The atoms, it depends on their relationship, right? We were talking about in the periodic table. These are all row 2 elements, right? So the more, since C and O are in the same period, right? So they're in that same row on the periodic table, you use electronegativity. Because when you are dealing with one row of the periodic table, the atoms are very close in size. And so even though oxygen is going to be a little smaller than carbon because atomic radius decreases as you go to the right, the difference in size isn't that big. So if you were comparing row 2 elements to each other, you go based on electronegativity, right? So the more electronegative element, the more stable. But you have to put that note in there, right? And let's change color to really make this emphasis, or to emphasize this. This is 4 elements in the same row. Now, why am I going so hard to emphasize that? Because the rule is different if the elements are not in the same row. So if we are comparing, and let's just stay in blue for now. It's just a lot of red. If we're comparing propanol with propane thiol, we're going to do the same thing. Draw the conjugate bases. We're going to remove a proton. That is going to give us another lone pair on that oxygen and a negative charge. Sulfur is also an element with 6 valence electrons, so it has the same bonding pattern as oxygen. When we remove the proton, we get an extra lone pair and a negative charge. Now, when you consider the periodic table, so we'll draw this back in here again, boron, carbon, nitrogen, oxygen, fluorine. Sulfur is right here. Sulfur is in period 3. When you think about the trend of electronegativity, oxygen is more electronegative. But the rule about the atom is which element can hold the charge better. And when they're all similar in size, like in row 2, electronegativity rules the day. But if, well, not why, I'm sorry. If the elements are in different rows or different periods, the larger atom is more stable with the charge. If charge is inherently unstable and being able to spread the charge out is stabilizing, the difference in the atomic radius as you go down the periodic table, so as you go from period 2 to period 3, oxygen to sulfur. Sulfur is just so much bigger in comparison to oxygen. It has more room for those electrons to spread out, that even though it has a formal -1 charge, it's going to be more stable than oxygen. So in this case, sulfur is actually more stable, which means it's the weaker base. We'll just fit that in here. Which in turn means that this would be, not more. That's not the word I want. This would be the stronger acid, right? So just to recap, read on this slide. If the negative charge is on a different element, then you can use atom, right? If the atom is in the same row, use electronegativity. If the atoms are in different rows, if they are in a column together, for instance, then you use size. So it's important to recognize that A is split up into two rules, but that is what you look at first. Check the atom first that carries the charge. Okay, but what happens if, and then this just ran through the making the decision that we did a few moments ago. But what if the charge happens to fall on the same element, right? This is where we're going to get into R for resonance. This is why we talked about, one of the reasons we talked about resonance so much in chapter 2. When we compare ethanol to acetic acid, we are going to do the same type of analysis. We're going to show the conjugate base, right? That oxygen goes from having 2 lone pairs to 3 and a negative charge. I'm going to draw the lone pairs in here. This oxygen also goes to having 3 lone pairs and a negative charge. So the negative charge is on oxygen in both of them. So A doesn't help us, right? We can't, oxygen and oxygen are the same. So then we go and we say, can those electrons, can that charge be spread out through resonance? Something to remember is resonance is stabilizing. So when we look at ethanol, there is no ability for resonance. You want to remember that there are hydrogens here. You cannot move those electrons off of that oxygen without violating the octet rule or breaking a sigma bond. However, with the acetic acid, you have one of your patterns that you learned in chapter 2. I don't know why I keep doing that. One of the patterns that you learned in chapter 2, where you have an allylic lone pair, right? So we can pop those a lone pair on the negatively charged oxygen to form a new pi bond, and we wind up moving, or just showing another way that this compound can be represented, in which that negative charge is shared on the other oxygen, right? If resonance is stabilizing, and this compound, the acetic acid here on the right, is resonance stabilized, this one's going to be more stable. If it is more stable, that means it is the weaker base, in turn making this the stronger acid. All right, so resonance can be a great stabilizing effect. Before we get into induction, I want to show you another example. Number of resonance structures can also make something more stable. So for instance, let's say we were comparing this alcohol here to this alcohol on a benzene ring. Right? Very similar. If we draw the conjugate bases, both of them have the ability to share. Sorry, we'll get that drawn out here. All right, so there's the acids we're comparing, and here's our conjugate bases. In one scenario, you have one resonance structure. I'm going through this quickly because right now we're studying acids and bases, and you guys did resonance practice in chapter 2, right? It can share that negative charge with the one carbon, whereas this one, let's draw it this way. So It can share with, I'm not going to draw all the resonance structures here because I'm going to run out of room, and I'm hoping that the point will be communicated. But this can continue, right? It creates another allylic lone pair. So that negative charge, I'm going to put my resonance arrow here, can be shared not only with that one carbon to the right, it could also be shared with this carbon here on the bottom. You could keep going and share with this carbon here on the left, right? And so it can continue on. They both experience resonance, but one has more resonance structures than the other, right? So on this side, we have more resonance. If resonance is stabilizing, more resonance structures are going to be more stabilizing. There's more atoms that can share the sort of the pain of that charge, right? The instability of that charge. So it makes it more stable. When it is more stable, what do we say? That makes it the weaker base. And the weaker base corresponds to the stronger acid. All right, so when we are analyzing structures for acidity qualitatively, we're going to check for charge. We're going to check what atom the charge is on. If we can't make a decision from that, we're going to check for resonance. More resonant structures are more stable. If that does not help us, then we can check for the inductive effect. So if atom and resonance fail you, so for instance, if we compare acetic acid with trichloroacetic acid, we're going to find that atom and resonance don't help us here. Conjugate base. You are going to remove the proton from the acetic acid. Have a negative charge. You are going to remove it from the trichloroacetic acid, negative charge. The charge is on an oxygen in both cases. Both of them can form a resonance structure, but just one, right, where the negative charge is on the other oxygen. So we'll just draw those out real quickly. Right, negative charge on the other oxygen, and we have chlorines. All right, so A and R don't help us. The inductive effect has to do with sharing electron density instead of through resonance structures, instead of through pi bonding, it's sharing electrons through the sigma bond. So you're going to go back to thinking about electronegativity. Chlorine versus hydrogen, right, is really the only difference we have in these two structures. And chlorine is a lot more electronegative than hydrogen, than carbon, than, not than oxygen, but the other elements. And so you are going to get some pull of electron density to the other side of the molecule from those chlorines. Whereas the hydrogen has this electronegativity very similar to carbon, it's not really going to be helping, right? If you have kind of this like cloud of electron density over here, this negative charge being shared on those two oxygens, the chlorine is going to help pull a little bit of that electron density away. So inductive effect is not as important as resonance. That's why you look at it third. But if all else is equal, the inductive effect can help you to see how the trichloroacetic acid could be more stable because it does have some help from those chlorines, trying to spread that electron density out a little bit. Again, making it the weaker base. The weaker base comes from the stronger acid. And we can see that this is an effect that can build up. Look at the comparison of pKa from acetic acid to trichloroacetic acid, but increasing the number of chlorines. One chlorine drops the pKa from 4.75 to 2.8. Adding another chlorine drops it down further, and adding that third chlorine drops it down even further. All right, so the more electronegative elements that you add, the more stabilizing it can be. Proximity is also important. So, for instance, if we were going to compare, let's see, putting a chlorine right next to the carboxylic acid versus putting the chlorine a carbon down. This one is going to have a stronger inductive effect because the chlorine is closer. So this one would be more acidic because that chlorine would help stabilize the base a little bit more than this one here. All right, so the number of electronegative elements and the proximity to the charge. Right, so the closer they are to the proton that is being removed. Now, those are the 3 rules that you are going to use most frequently as you're working through Chapter 3. Atom, resonance, inductive effect. But there is one last one we need to talk about, and that is orbital. This really comes down to comparing hydrogens that are, or protons that are attached to carbon that is sp3 hybridized, carbon that is sp2 hybridized, and carbon that is sp hybridized. And it's because that sigma bond, the main difference in those 3 CH bonds are the orbital shapes. sp3, sp2, sp. So when you remove the proton, right, because we're always comparing the conjugate base, you're going to get a lone pair here or a lone pair here. That lone pair is going to wind up, that charge, that, where that charge is localized, that lone pair is going to be either in an sp orbital, sp2, or sp3, and they have different shapes. The sp orbital is a little bit rounder, but it's also a little bit tighter, or the whole thing is closer to the nucleus, right? And the closer to the nucleus those electrons are, the lower in energy they're going to be, right? So sp is going to be more stable than sp2. This sp2 is going to be more stable than sp3. So what does that tell us? That means hydrogens that are attached to carbons that are in triple bonds are more acidic than hydrogens attached to carbons in double bonds. And they're both more acidic than hydrogens attached to carbon that has all single bonds. All right, so if we were comparing, so instead of 2 different compounds in this slide, we're looking at hydrogens in the same compound, but you're following the same strategy. You're looking at the conjugate base, right? If we remove the red proton, we have a negative charge on a carbon in a double bond, so an sp2 hybridized carbon. If we remove the blue hydrogen, we get that negative charge on the carbon in the triple bond. They're both on carbon. There's no resonance here. There's no inductive effect at play. There's no like chlorine nearby. So the only difference is that orbital where that lone pair negative charge is. And so the thing you really have to remember is that, let's see, the sp-CH bond is more acidic than the sp2-CH bond, which is more acidic than the sp3-CH bond. And you can see that when you compare pKa's, right? Okay, we came up with that this one was more acidic because it was on the triple bond. When you compare the pKa's of ethane, ethylene, and ethine or acetylene, the pKa's are drastically different. Now, none of these are considered acidic. 25 is not a low pKa, right? Some of your strong acids have pKa's of like -9. But compared to 50, right, the the SPCH is much more acidic. And that's actually going to be really important to us in chapter 9 when we talk about alkyne chemistry. All right, so we talk about all of these acid-base issues early, and then they come up again for us throughout the year. All right, and here we go. We are just going to summarize generally using ARIO. Now, I'm going to finish up this discussion and continue on in the next video.